Welcome everybody, and Jose is going to tell you what we're going to see.
Oh, well, yeah, so welcome everybody. Yeah, happy to introduce my student Douglas. We started working together, when was it, like 2017, I think? Maybe we had some reading courses before then. I was always very enthusiastic to get started working on this stuff. I actually had to kind of, or I didn't have to, but I thought I should give him a chance to kind of shop around, see if he could find a better deal and an advisor, but he's for some reason he came back. Yeah, we jumped right in, really. This isn't a very beginner friendly area. I think that talk will reflect that a bit, not because it'll be hard to follow, but you'll see that there's a lot of ingredients that go into all of this stuff. But he jumped right in. We started studying some really kind of exotic, interesting classes of C-star algebras. You'll see that, I don't want to steal his thunder, I guess, but you'll see that it's kind of broken up into two parts. The first part was, this class of C-star algebras that we started looking at. And then the second part, he has to do with a question that I asked with a co-author in a recent paper that Douglas managed to answer. So you'll see that they're kind of independent but related. And yeah, I'll leave it at that and let Douglas tell you the rest. Go ahead, Douglas.
Thank you, Dr. Carrion, and thanks for the last 4 or 5 years. So I'll begin by explaining what a algebra is, since that's something they don't do in algebra class or even in algebra class. It's a combination of a ring and a vector space. So in addition to addition, it has multiplication within the set, as well as by some scalars from some field. A star algebra, the field is the complex numbers. So we introduce another operation called involution, which is based on complex conjugation and where the star comes from. To get a C-star algebra, we need a norm, which measures the size of the elements, and it has to satisfy a special property which looks innocuous, but is actually very powerful. So for C-star algebras are a topological version of a measure theoretic thing from Murray and von Neumann called rings of operators, but which are now known more as von Neumann algebras. They were given an abstract characterization by Gelfand and Naimark, and their name by Siegel. One of the biggest questions about them right now is, what does the C stand for? So that's background. For an example, the continuous complex valued functions on a compact Hausdorff space form a C-star algebra just using the regular old operations, just doing it pointwise. For the norm, we use the sup norm. When in the simplest case, when x is just a single point, we get back the complex numbers. But in most cases, we're going to get something that's infinite dimensional. So even though this slide says example abelian C-star algebras, this is actually all of them. There is a constructive bijection between these compact Hausdorff spaces and unital abelian C-star algebras. X is fully described by C of X. So when we're looking at it, we're really doing topology. These abelian C-star algebras are very well understood, since it's just topology, which makes them very useful for understanding non-abelian ones, which we could call non-commutative topology. Another familiar example are the n-by-n matrices, complex matrices. Again, we're going to use the regular operations, but involution, we don't just take the complex conjugate of the entries, but we want it to be anti-multiplicative, so we also flip the matrix along the diagonal. The norm you might not have seen before, it's called the operator norm, and it measures the largest factor by which the matrix scales a vector when used as a linear operator. once again, in the simplest case, when n equals 1, we have complex numbers. But in any other case, we're going to get something non-abelian, since matrix multiplication isn't commutative. And another parallel with the previous slide, there's actually simple finite dimensional C-star algebras are uniquely determined by their dimension. So we had the rings of operators. Now we have the operator norm. Clearly, operators are important, and that's not just because my name is Wagner and it has the word opera in it. In fact, the n by n matrices are just the bounded linear operators on n-dimensional vectors, complex vector space. And for many complex Hausdorff spaces, such as the unit interval, the continuous functions form a star subalgebra of operators on the square integrable functions. In fact, any closed star subalgebra of bounded operators on any Hilbert space is a C-star algebra. Hilbert space is just a vector space where we have an inner product, which is where we get a norm and our involution. And clearly they're a rich source of example C-star algebras. And in fact, in a seminal theorem by Gelfand and Naimark, it turns out they're the only source. Every C-star algebra is an operator algebra. But that doesn't mean we have to start with the Hilbert space. We could instead start with a discrete group. We'll use the group operation as our multiplication, and inversion of elements as involution. And for the vector part, we'll just pretend it makes sense. So we get this star we get this star algebra of formal finite sums. We still need a norm though, and so we'll use the Gelfand-Naimark theorem to get it by just having this operate on some Hilbert space, such as the square summable functions on the group, using what's called the left regular representation. Taking the closure then gives us the reduced group C-star algebra. The details of this representation don't really matter for now, but you'll get if you pay attention, you'll get an idea of what it is later. But you can think of it of how a group can act on a topological space, such as the integers acting on the unit circle from using 90-degree rotations, which gives us this picture with cosets of 4z. Or something more interesting, it could rotate by e to the 90th degrees. Since this is irrational, the action ends up free, and we get this picture which looks like a Cayley graph. So when a group acts on the topological space, it's also acting on the functions. And we can create a C-star algebra which bundles up the group and its C-star algebra, as well as the continuous functions. And it even contains the information about the action, which can be reproduced through conjugation. So this bigger C-star algebra is called the cross product, the reduced cross product. And it's similar to the semi-direct product of groups, if you're familiar with that. So we got the reduced C-star algebra from the left regular representation, but we could use different representations, and that might give us different C-star algebras for the group, or even different cross products. But that's only true if the group is not amenable. In fact, the uniqueness of the C-star algebra could be taken as the definition of amenable. Another definition is that the group has you can find finite subsets within it whose insides grow faster than their border. So remember, we're talking about discrete groups. So actually this is z squared. We're just zoomed really far out. And you'll see these green circles are displaced by the same amount from the orange circles in each picture, but the intersection of the two begins to dominate. So amenable groups include all of your favorites, abelian groups, finite groups, and basically anything you can make from those. Really, you can take the name amenable literally. A group is amenable if it's easy to work with. For example, they admit invariant measures. When a group is not amenable, you can split it into two halves, which would both have the same measure as the whole group, a la the Banach-Tarski paradox. Everyone's favorite example of a non-amenable group is the free group on two generators, which, if you're not familiar with it, here is a Cayley graph. And if you're not familiar with Cayley graphs, really it should be directed, but it makes the picture too cluttered. But each of these vertices correspond to a group element, and these colored edges correspond to different generators. So we have an element here, which is up, right, down, and it's a different element from down, right, up. These generators don't commute, but the element up, down, up is the same as the one that's just up. And you can see from this fractal-like structure that there's no way to really get around to get a big inside. Hence, it's non-amenable. So in part one, I looked at a set which every group is able to act on, and that is the group's own set of subgroups, just from using conjugation. So the orbit under this action of a subgroup lambda is denoted O lambda, and it's just the set of conjugate groups. We then attach a topology to the set of subgroups, which is defined naturally and makes the action continuous, but I won't give the exact details. We take the closure of the orbit under this topology, and we get the orbit closure mentioned in the title. These orbit closures can be thought of as kind of like a generalized form of a normal subgroup. If we have a normal subgroup nu, then its orbit closure is the singleton of just nu. Also, this action can never be free, meaning not every point is going to be moved by every element. I mean, clearly, a group is going to remain fixed when it's conjugated by anything that it contains. So we can't get the action free, but what if we can get it as close as possible to free? What if the only things that fix subgroups are the things that the subgroups contain? Instead of free, we'll call this cheap. And it means that every subgroup in the orbit closure is equal to its own stabilizer. This also leads to the definition of topologically cheap, where every subgroup is equal to its own topological stabilizer. So this idea of cheapness is the same concept as genericity for a uniformly recurrent subgroup, or URS. A URS is just a orbit closure that is minimal, meaning it doesn't properly contain any other orbit closures. URSs were defined by Glasner and Weiss as a topological version of a measure theoretic thing, which if that sounds familiar, it seems to also have been to Gabor-Elik, who used URSs to create a new kind of C-star algebra. And one C-star algebra he made from them was able to answer an existence question. So a trace you can think of as like the trace of a matrix where you add up its diagonal. Amenable is related to the group definition. It mostly just means it's a nice trace. And the rest you don't have to worry about. Point is that it's a new and exotic C-star algebra with interesting properties, strange properties, such as it's not exact. I'll get back to exactness in part 2. But I wanted to see if we could create other strange C-star algebras and answer more questions. But in order to construct these C-star algebras, we have to understand the relationship between the cosets and the conjugate groups. Obviously, lambda is going to be contained in both, but there's also an invariant map where we just take the coset and multiply by its inverse. An equivalent definition for cheapness is that this map is reversible. When we have a finitely generated group, we can impose further structure on the cosets by constructing a Schreier graph, which is like a Cayley graph, but instead of the vertices being group elements, they are cosets. Our C-star algebra is going to act on the L2 space of these cosets, and it's built up from local kernels. I won't give the exact definition of a local kernel, but I do want to give an intuition of what they're like by showing an example, which we'll call K. So this represents a Schreier graph. So each of the vertices is a coset, and the edges are generators that lead between them. K is like a matrix whose rows and columns are indexed by these vertices. So each vertex has its own column and row, like this gold one has its own column, which I've color-coded, as well as its own row. So this dot here lies along the diagonal of K. So within the gold column, each vertex has its own row, but what are their values? Well, the local part of local kernel comes from its finite width, which K will say has width 1, which means it's going to be looking at balls of radius 1. So the radius 1 ball around the gold vertex is this gilded subgraph, which contains every vertex within one edge of the gold vertex, as well as all the edges that connect them. So the vertices within this subgraph are the only rows in the gold column that are not 0. So K is like a banded matrix. It vanishes when far away from the diagonal. So these values come from the vertices, but there's a reason I wanted to include the edges within the definition of this ball. And that is, if we look at this silver vertex, the radius 1 ball around it is actually the same as the gold ball. You see, they both have these black triangles. They have these 3 red edges around the perimeter, a blue edge, and a green edge. So the silver vertex is going to have its own column within K, and we can go ahead and fill in 0 for everything not within the silver ball. But within that ball, within the band, it's actually going to be the same as within gold's ball. So, for example, in the gold column, the entry of the row of the vertex connected by this green edge, which I've highlighted for you, is A, and that's the same value as this entry within the silver column, which corresponds to the row of the vertex, which is connected to the silver vertex by the green edge. So K is very local. It only looks at these balls. That's all it knows. And there's only finitely many of these balls. You'll note that the graph itself depends on the generators we choose for the group, but that actually doesn't change what is a local kernel, just maybe what their width is. And so it doesn't change the C-star algebra itself. So I started by expanding upon what Ellick has already done. When our orbit closure is minimal, then the following are equivalent. The C-star algebra admits an amenable trace. The C-star algebra admits a faithful amenable trace. And the group acts amenably on the cosets. So an amenable action means that it's easy to work with. In particular, if a group is amenable, then it always acts amenably. I also got this intersection result, which is a hot topic within C-star algebras. For any non-trivial ideal of the C-star algebra, there's going to be a non-zero intersection with the continuous functions on the orbit closure. So these intersections correspond to orbit closures within O lambda bar. So when a O lambda bar is minimal, it's not going to contain any other orbit closure, so the C-star algebra won't have any ideals. So while I was working with these, I noticed an interesting property of these C-star algebras. Remember, they're similar to normal C-star algebras, normal subgroups. Orbit closures are like normal subgroups. So if you look at the C-star algebra of the orbit closure of a normal subgroup, the Schreier graph just becomes a Cayley graph, and we get back the reduced C-star algebra of the quotient group. So a secret about C-star algebras of groups is that they're all actually cross products with the complex numbers. And something I told you about the complex numbers is that they're just continuous functions on a singleton set. Don't worry about this intersection business. It's a technicality that we can ignore in practice. But we have that the C-star algebra of the orbit closure of a normal subgroup is just a cross product of the continuous functions on its orbit closure. And in the general case, this isn't true. In fact, I showed that outside of the normal case, it can never be true. However, it does contain, the C-star algebra of the orbit closure does contain the star algebra of this thing that we can assume is just gamma and the continuous functions on the orbit closure, which if you were observant, you noticed that the previous slide doesn't make sense without that fact. And it also, again, contains information about the action on the orbit closure, which means it's like a cross product. And that gives us some tools to work with, such as a definition which isn't reliant on Schreier graphs and thus can be extended to non-finitely generated groups. It also has led to several other results, maybe a highlight of which is that a subgroup is topologically cheap if and only if the continuous functions on the orbit closure is a Cartan subalgebra of the C-star algebra of the orbit closure. So a Cartan subalgebra is a special kind of maximal abelian subalgebra. And as we talked about earlier, abelian C-star algebras are useful for understanding non-abelian ones. There's also this special case, a subgroup is cheap if and only if the continuous functions are a C-star diagonal subalgebra, which is, you can think of as like the diagonal subalgebra of a matrix algebra. For part two, we looked at, in part two, I'm looking at the decomposition of nuclear star homomorphisms. So this is similar to a non-commutative version of a partition of unity. A star homomorphism is your basic morphism for C-star algebras. It preserves all the operations and thus contracts the norm. We call it nuclear if it can be approximately decomposed into these maps downward into finite dimensional C-star algebras and then upward into out of the C-star into like the image of the star homomorphism. So these maps are weaker than star homomorphisms. They're contractive completely positive, which means they don't preserve multiplication. Well, they could, but they don't necessarily preserve multiplication, but they do preserve some of the order structure. So I'm finally gonna get back to exactness, which is when pi is injective. Now this definition is actually reliant on the range B. So there's a strictly stronger definition of an amenable C-star algebra, which is when B is equal to A, and this is just the identity map. So examples of amenable C-star algebras include all your favorites. Abelian C-star algebras, finite dimensional. Abelian, we saw on the previous slide. Finite dimensional, we don't even need the decomposition, and anything constructed from those. It also includes C-star algebras of amenable groups, and that is yet another equivalent definition for an amenable group. So these maps lack multiplicativity, and our goal here is to see how nice we can get them. Can we get something like multiplicativity? Previously, in the amenable C-star algebra case, Hirschberg, and White found that the downward maps can be chosen to be convex combinations of order 0 maps. Order 0 means that it preserves multiplication when the product is 0. Ergo, it preserves orthogonality. Later, Blackadar and Kirchberg found, again for amenable A, that we can get the upward maps to be approximately multiplicative if exactly when A is also quasi-diagonal. So quasi-diagonal, the definition is like that for an amenable C-star algebra, but instead of having maps that go back up, we instead require the downward maps themselves to be approximately multiplicative and approximately norm preserving. So Brown, Carrion, and White were able to combine these two results, and then Carrion and Schaffhauser extended the first result to cases when A is not amenable. And what I sought to do is see what else can we get when A is not amenable. And can we get the rest of it? And I was successful when A is exact, which is what you're gonna encounter on the streets. So if we have an exact C-star algebra and a star homomorphism to another C-star algebra, Then we have these finite dimensional C-star algebras and these maps to and from them, such that the CCP maps approximately compose to the star homomorphism. The downward maps are convex combinations of order 0 maps, and the upward maps are approximately multiplicative. If and only if pi is nuclear, pi is quasi-diagonal, which means it can factors through a quasi-diagonal C-star algebra. And we have this stuff about quasi-diagonal traces, which are like amenable traces. And that is, part 2 is much shorter than part 1. So that's the end.
Right. Thanks a lot. So I guess I'll be corrected, but how this will work is we're going to go into a breakout room, the committee and Douglas will, but in a minute to ask some questions, but maybe I'll stop here. I don't know if there's any kind of general questions from the audience about the presentation itself, and maybe Douglas can answer some of those if there are any. So audience minus the committee. Well, I wasn't necessarily expecting any, but just in case. Well, anyway, let's thank Douglas one more time.
Okay,
All
so I
right.
guess I'll put you guys in a room, okay? The committee.
Yeah, Ken will quarantine us.
Yeah. We still believe in you, Douglas. Don't let them get you. All right, here we go. And everybody else knows what to do now. Yeah, Douglas, you need to join.
Oh, I go in. Okay. How do I?
Yeah, you should have had a message, Douglas. Click on breakout room. There you go. All right. Great. All right. Time to change. Dang, Alyssa, that's pretty good.
I'm at the office and I didn't have any work shirts that were orange. So we're going to do background and balloon.
That's cool.
Most impressive.
I mean, I'm slightly colorblind, so I can't always tell, but it looks like Marcus actually painted his room for Douglas. I mean, that's impressive.
I think that's true. Yes.
Yeah. Yeah.
So good to see you all.
Yeah, Shaylin, where are you zooming in from?
I'm zooming in from Nairobi, so it's getting close to my bedtime.
Wow.
Yeah.
And I'm afraid I chose my laptop where the camera doesn't work. So sorry, you can't see me in my orange shirt, but excited to celebrate with Douglas.
Hey, you could change your picture to something orange and then.
Ooh, let me see if I can figure out how to do that in however much time I have.
Yeah.
Yako, how was California? How was California?
It's really nice.
Is it?
Yes, the weather is perfect year round, so I'm not complaining.
And so tell me what you're doing.
What's that?
Tell me what you're doing.
Oh, I'm teaching
Okay.
at a university around here. All virtual since, oh my God, it's been a year.
Yeah.
Only on
Us
Zoom.
too.
Yeah.
Yeah, I heard. Some classes started in person, but it only takes like, I think 25% capacity of the classroom. So yeah, it's been weird.
How's James doing?
He's doing good.
Okay.
He's enjoying his duty without deployment. It's nice weather, so it's a nice
Cool.
break after long years on the ship. So
Cool.
are all math classes at TCU virtual?
Right now they are, and but in the fall we're gonna do in person, but extremely spread out in person.
Oh,
Yeah. So like I'm teaching I think a 30-person class, but it's in a lecture hall. So, you know,
oh wow.
yeah.
Spreading out both by time and space.
Yeah.
Yeah.
So like certain students can come on certain days, but not on certain days. Like, do they switch?
Well, I think at least the ones I'm in, they come every time, but it's just a very big classroom.
Ah, I see.
Yeah.
But they're also pushing classes into the evening
Yeah.
Ah, I see.
to
Yeah.
make more space.
Okay. Interesting. Let's see.
Hey, Shaiga, so what's up with you at Virginia Tech?
Yes.
See there?
There he is.
There you
Orange now.
Yeah.
Yeah, I cannot see my background.
Oh,
It's
weird.
orange.
Yeah, it's orange. Yeah.
Hello. Yeah, so yeah, it's getting better. So yeah, I taught all hybrid classes, so it was pretty much like face to face.
Mhm. Oh, okay. So how many of your students actually came in person? Like what percentage?
So like all classes are split into 3 groups. Each group meet like once a week. So
I see.
yeah, so some people meet on Monday, others on Wednesday, and then Friday. And if someone gets sick, they can actually, so we have to organize one online. They can attend that one. So
Yeah.
That's how it is going.
Yeah. Okay, Ivan, that's pretty good. Oh, Dennis is trying to one up us. Look at that. Oh,
It's the orange song.
yeah. Good stuff. Does everyone have your sparkling beverage ready? Unfortunately, I've just got Topo Chico, but it's
Sparkles.
yeah. I can't tell, is that red or orange? The
You know what? For today's purposes, it's orange all the way.
It's like that Valerie's going all out and not only has an orange shirt, but an orange cat.
Yeah.
Yes.
That's some effort, man.
That's exactly right. That's
Yeah.
exactly right.
Yeah.
And he is just purring with pride.
I bet the cat really enjoyed the nuclear C-star algebras and stuff.
You know, I had to ask him, I whispered in his ear to explain it to me. And yeah, he really simplified it for me.
They're so smart. It's amazing.
And Bob and Shirley, it's so nice to see you.
Nice to see you all. Thank you.
What's your kitty's name?
His name, I always have to preface this, Shirley, because he's actually not our cat. He's our we call him our temporary cat. So we did not name him, but his name is Shiner. And not after the sun. But he is a very, very sweet cat, and we don't hold it against him. He belongs to one of our daughter's friends.
Okay.
We kind of got in a situation where she and her husband had to move in with in-laws, and in-laws were happy to have them, but not happy to have
Oh,
Diner. So anyway, we have enjoyed him. He's a very good cat.
So Bob and Shirley, what's new?
What do you want to know?
Everything.
we're existing.
Yeah, I'd really like to see this C-star algebra stuff continuing on at TCU, as you might know.
Yeah.
No kidding. That's great. But
Finding any more golf balls in your backyard?
I lost all my palm trees. It turned out to freeze.
Oh, really?
Yeah, I've been
Yeah.
working hard on that. 30-year-old ones.
Oh,
Yeah, it really wiped them out. So, in fact, I spent this morning digging out the roots of a bunch of them.
mhm.
So Ken knows about those. Some of you, I don't know who else knows. Jeff knows, Jeff Bond. Some have been out here, but I.
Oh, well, no, almost everybody's, because you've
Has
had your
everybody
parties
almost been
before.
out here? Okay.
Yeah,
Mhm.
Well,
a
that's
lot of people.
wonderful. Great.
yeah.
Yeah,
I remember
Busy.
Shy God had a great basketball game over at your
that's
house.
true.
Yeah. Yeah. Yeah, those of you who don't know, Bob, that was his field too, C-star algebras, and he wrote this big gigantic book on C-star algebras. So
Yeah, it's beautiful stuff.
yeah. Yeah.
Scott, you're looking good.
Oh, thanks.
You don't have your tongue out at least.
Yeah, I also got sunburned over the weekend, so I'd look more orange for Douglas's reception here. So
You could get some tips from John Boehner.
yeah.
That's right.
Yeah. But, anyway.
Melissa, how's Victoria?
It's been definitely interesting here. First year has been a lot more work than I thought it would, but I'm excited to see what the next year brings. Lots and lots of small classes. I'm teaching in person mostly. We're doing, I think we call it hybrid. I think you guys call it something else, but or alternating. I think we call it alternating. You guys call it hybrid, something like that. But half the class is supposed to be in class, half is supposed to be at home on WebEx. And that's all supposed to be, because most of them decide to stay home on WebEx anyway. WebEx is our version of Zoom. Uh-oh, time to go.
So Shy God, does that happen to you too, where a lot of them just stay at home the whole time?
Not with me. I'm pretty hard on them.
Uh-oh.
Hi, Douglas.
Hey, Douglas.
I'm liking the backgrounds.
Well, as soon as the committee comes back, we'll
That's just.
have to break it out.
You should have done it. You should have made it say orange, but in a different color.
Oh no, it's the orange song. So
You have to wait for it. Yeah.
it lists things like a pumpkin's orange, an orange is orange, so a carrot's orange.
Cheddar cheese,
Then why aren't you singing it for us?
basketballs.
I've never heard it. I just went to YouTube and just downloaded it. I don't even know how it goes. So like how you supposed
I
to.
assume it's for
No,
children.
yes, it is.
And C-star algebraists, actually.
Yeah, correct.
Yeah,
Yeah, yeah.
right, yeah.
They at my thesis defense, everyone showed up in orange as well.
Oh, really? Cool. Yeah, he has a master's thesis from University of South Alabama, so. Yeah, I mean a master's degree, yeah. So that's cool. So did they ask you any hard questions?
No hard ones.
Okay.
So how do you feel? Do you feel like 1,000 pounds lighter?
Not yet.
Not yet?
They're trying to make you nervous right now.
Do you want us to also bite our nails for you? Is this like nail biting moments?
Did you see, Douglas, that Valerie even brought her orange cat to the talk?
Yes.
Yeah.
He's gone.
I see Marcus painted his walls.
Yes. Yes. That's such dedication. It's
That's
amazing.
right.
You've made such an impression on him, you know? Yeah. Yeah.
Did Tamara have to leave?
Yeah, I think she must have had to go teach, but yeah.
Thanks everyone for coming.
Yeah.
How y'all doing?
Hey,
How-
Isai, tell
how's
us what,
school?
you notice Isai, yeah, Shaylin's here from Kenya, Nairobi, yeah.
I am. Congratulations, Douglas. Sorry, my camera's not working, but you can imagine all of the orange all around me. In fact, I brought a giraffe. It's right here. just to celebrate.
Are giraffes yellow?
Some of them are orange. This one is
I
orange.
need to get an,
You can
I need to get
imagine.
an orange one. When I was in first grade, I got in trouble for coloring a squirrel orange instead of brown. And I argued with my teacher that there are orange squirrels. And
Wow.
that was before the internet was commonplace, so you couldn't just look it up for evidence. But there are bright orange squirrels in Europe.
Really? Huh.
Yes.
Oh.
Oh, here he is.
So the orange goes back a long way, huh?
Yeah.
There's a kitty.
Ever since I
She loves the kitty.
Good distinguished
I
color.
don't even remember. Pretty much always, it's been my favorite color.
Tiger.
I have it so much because of my brother. I have a younger brother who's about the same age, and so we would designate whose stuff is whose by I would have orange stuff and he would have blue stuff.
Oh.
And so I just continued that.
Cool.
Well, Douglas, my only regret is I was never able to find orange pens for you.
Oh, no. These are the graduate students.
I did get a case actually.
Did you?
Yes.
So what are your plans? What are you going to do tomorrow?
Catch up on the stuff that I haven't been doing because I've been preparing.
Yep.
Need to work on Dr. Pucketer's class.
Cool stuff.
Today I'm getting vaccinated.
Ooh, really? Wow.
Mhm.
It's your first one, huh?
Yeah.
Cool.
How
Yeah,
many
Leah
of
just-
you, how many have been vaccinated in this group? Quite a few. Wow, that's good.
Yeah.
Me
Leah
too.
just got her second yesterday and
I see.
she's got a fever today.
My goodness, okay.
Yeah.
Now Shirley and I, we're old people, so we had ours a long time ago, both of them.
Yeah.
Yeah.
Good job.
We are old people, compared to this group.
Never.
Yeah.
Yeah.
Ken didn't say it. Chair for 21 years there at TCU.
That's That's right.
And then my last PhD student was in 1980. That was Ron Morgan, and he wrote it on Szymanski properties of von Neumann algebras, which nobody knows what that is, but that's okay.
And if you guys want to know what Bob was like and Shirley, they looked exactly the same as they do now, you know, many years ago.
Wow.
Yeah.
Yeah, Shirley, that's really good.
Yeah.
That is
Hey, so
great.
what's the
Well-
verdict, Jose?
It was a unanimous vote, so congratulations, Douglas.
Hey,
Okay,
I don't know if we
break
get to
out the
call you
sparkling
Dr. Douglas
beverages.
Wagner yet, but congratulations.
mhm.
Cheers.
I'm sorry I didn't wear any orange, Douglas, but I didn't bring any out to Washington State, so.
You're in what? Where? Seattle, Portland?
Yeah, north of Seattle, in Bellingham.
I have a sister in Seattle.
Oh, so many people have relatives out here. It's
It's
very nice.
actually somewhere I'm considering moving to.
What?
Oh,
Yeah.
very
I didn't
cool.
know that.
Yeah, well, you can't stay with us, so sorry, it's nothing personal, but we already told the kids that, so we can't let you in.
Darn, I was actually really hoping to get a remote job, so I don't have to move.
Actually, that's interesting. Is that an actual possibility?
Well, it's one of the places I'm looking at jobs in. Like it's not, I don't think I've, well, actually, yeah, I have a interview Thursday with a company in Seattle.
Cool.
Wow, well, good luck with that.
Yeah.
Yeah, I guess remote work is here to stay.
Yeah. I really appreciated the opera comment. Douglas. That was good. I hadn't heard. Was that the first time you've used that one?
No,
Oh, okay.
Isai might have seen it before.
Oh,
I
okay. Okay.
pointed
Yes.
it out right when I was getting into Dr. Carrion as my advisor.
Oh.
I'm like, clearly this is meant to be.
Yeah, so I actually had a question about that. I was wondering if any of your research had any applications to the ring cycle.
I actually haven't seen the ring cycle, but I have seen the Flying Dutchman.
Okay.
And I know the story of the ring cycle.
Right, as long as someone's wearing a horn hat, that's close enough.
And it probably has applications to physics,
Hey, Kitty.
you know, too.
Oh.
based on- Oh, wow. Yefton, you really need an orange background to go with that.
Yeah.
It'd be like Halloween.
Yes.
Yeah,
Yeah.
after your cats love your back.
This one
Obvious.
especially, yeah, she showed up when Jose and I were running the Brazos analysis seminar. And I asked him, should I turn my camera off? He said, no, that's more interesting than the slides.
Right.
Yeah.
Kept the viewers engaged.
So,
Bob,
Dr.
Bob, how
Park,
are you doing?
What's that, Douglas?
Are you the cat?
Me and Lewin Davis we are the cat.
Douglas, congrats, but I gotta go teach, so bye, yay.
Have fun.
Bye, Alyssa.
Hi,
Thanks, Melissa.
Alyssa. So good to see you.
Have you seen that video of the lawyer who's not a cat?
I think
Yeah.
everyone on the planet has seen that video. All my lawyer friends sent it to me. So, and then Jose as well. So
You have a lot of lawyer friends?
yeah, unfortunately, almost all my friends outside of mathematics are lawyers. So don't cross me or you will be sued.
Wow.
Yeah, when I made a joke about that at a committee meeting, nobody had seen it. It was like a week after, but even so, that's when they would have seen it. And it just felt completely
Yeah.
flat. They ignored me completely. It's a crazy guy talking about cats.
Well, as Robin Foreman, Ken and Igor's advisor, once said, never not tell a joke just because you think some people won't get it. If it's funny, then throw it out there, and those who get it will get it.
Honestly, it was even funnier when they didn't get it. To see their reaction.
I tell a lot of jokes to myself.
Yeah.
Like that no one even notices.
They're so obscure, you don't get them.
But do you actually say them out loud, Douglas?
Yes.
Oh, okay, okay.
If I ever say something with a grin, it means something which you don't understand. Just now, I think. I forgot what it was.
So Ken, when is well, this is going to be interesting for everybody, but when are all these forms due? Do I need to do this today?
I think you can just do it over the next couple of days. Yeah.
Okay, it's not like
Yeah.
an urgent thing. I think I'll send some of them out today, but I don't want to.
Yeah. Yeah.
Oh,
The
cause
dean's
any
office
delays.
needs all these.
And
forms.
how does are there any so I know TCU is doing an in-person. I actually don't pay attention to any of these emails, but they're doing like an in-person graduation.
Yeah, I think Douglas is not going though, so.
Right, but exactly. But is there some virtual thing for like PhD students? How didn't, because PhD students, do they normally do their own thing, right?
Yeah, they normally have a hooding ceremony. And I actually haven't heard about it yet. So I don't know.
Yeah, I haven't got any emails about
Yeah.
anything like that.
Okay. If there is something, maybe let me know. Because
Yeah, I mean, we did it last semester, I think, and they did something like this, you know, on the Zoom or something.
No, if there's like a ceremony, I'll go. I mean, I'll do it. I haven't ever been to any. I never went to any of my own graduations.
Yeah.
But I feel like I should definitely go to this one.
Yeah, I'm actually kind of relieved I don't have to walk.
My advisor told me something similar. It was like, you know, I didn't even go to my daughter's graduation, so I hope you don't, you know. And I was like, oh, good. I wasn't planning on going either, so okay.
I wasn't going to go, but my mom made me, and like my advisor said, that is amazingly common.
Yeah, my dad.
It's the parents that usually drive this.
My parents were very eager to see me.
Yeah, at least for a virtual hooding, I wouldn't actually have to wear any, you know, the whole getup, right? I hope not. I could maybe do like a Zoom background with the Zoom getup and me just stand in the middle with my face inside the.
Yeah.
I don't actually own any.
Oh.
Yes.
That reminds me of.
I think reasonable.
Well, what the heck?
What's next, Jeff?
I can't figure out what's going on.
Ken, you're in charge, right?
I
No.
don't take that responsibility.
Let me try this again. Bob, how are you doing?
I'm doing great.
Oh, good.
Yeah, I'm getting better looking every day.
Well, that's for sure.
And Shirley's right behind me.
Oh, yeah. Shirley, how are you?
For those of you that don't know, I mean, she was at TCU for 26 years, you know, in the department too. She was we don't call them secretaries anymore, as administrative assistants. Okay.
I gotta blow it up. I can hardly see you there behind Bob on the tiny screen.
Yeah.
Sounds like someone needs a trip to the eye doctor.
She can get up there. She looks as good as ever.
I do. I was just about to get new glasses when all of this hit, and I'm out of date.
Well, how many fingers am I holding up, Greg?
You don't have any fingers.
I know a finger I'd like to
Gave it
hold.
away.
Well, David, thank you for coming all the way over here for this
Across the
defense.
pond, yes.
Very long trip.
That's good.
So
David, sure.
actually, where are you, David?
I'm at the University of Münster in Germany.
Oh, okay. Great.
So I just moved here in January. So I just started the new position.
Oh, okay.
Yeah.
Oh, see, I didn't know that. Okay.
Yeah, I
No
didn't
longer
know
in
that either.
Texas. Yeah.
Thought you were still at A&M.
Nope. Nope. I left A&M.
Okay.
What time is it there?
It's 8:30. Just the last little bit of daylight.
Very nice.
Great.
So how are things in Texas?
You know, as you remember them.
Yay.
Mhm.
Orange. It's not bad. I mean, in terms of weather, it's actually a nice time of year, unless you have allergies, which I do. So I get to look at the nice days from indoors. But I'm pretty
It's
happy. We
snow.
went, our COVID thing went from, I was saying, well, I don't want to turn the conversation to that, but we went from extremely high risk to just very high. And I think we're at just high now. So this is, it's looking good.
Yeah, it's actually going down quite a bit here. It
Yeah, in
hasn't-
Tarrant, yeah.
Tarrant County, everything's going down really nicely
Mhm.
because we have a good vaccination rate.
Well, Rhonda and I are getting our second COVID shots on Thursday. So if I'm not feeling well, Anne Marie is going to be teaching abstract algebra for the class. So probably should give her a heads up about that.
Sounds
I'll
good.
just send you the notes. It'll be easy.
If you guys have a book, just tell her the section. That's it.
Oh, actually, Ivan's here too. You guys could split duty. So yeah, I'll just see you guys can just like thumb wrestle decide who does what section.
Yeah, double team it.
Hey, Efton, how's your house coming along?
It's, well, we're Thursday is kind of, we're crossing our fingers, should be a triple letter day because it's Coco's second birthday and it's our COVID shot, and our windows are finally supposed to arrive. They've been delayed twice. So we're hopeful because, you know, they can't really do anything till we get some windows in. So we've been kind of waiting for that. And
Were they stuck in the Suez Canal?
no, it's you know, everything's blamed. COVID's the excuse for everything. So they're coming over from Canada and it's hard to get stuff across the border. And so there've been delays for that. But they're supposed to be here on Thursday. So we're cautiously optimistic. I don't know if we have
Really
any
hard
trouble.
to take them over the big wall without breaking them.
That's right.
Right,
They have to
right.
do it under the cover of darkness. And I know I can count on David to help us out if we run into any problems, since he's his other life as an architect. So I know I can count on him to step in.
When's Ken getting up there to install them?
Yeah, Ken. We got some hardy material that we're going to put up. So I mean, I said, I know just the guy. He'll work cheap. And
All right, well, thank you all for coming. Let's
Thanks for having me.
congratulate Douglas one more time.
Yeah.
Congratulations.
Good job, Douglas.
Congrats, Douglas.
Congratulations, Douglas.
Thank you.
well done, Douglas.
You guys have
Bye,
a good
everybody.
one.
Thank you for
Really
coming.
good to see
Thank you.
everybody.
Yeah, see you all.
Bye.
Bye-bye.
Thanks for coming.
Congratulations, Douglas.
Congratulations again, Douglas.
Thank you.